Hello, I welcome you all in this course on steam and gas power systems. Today we will develop a general relationship between different operating parameters in a nozzle, and supersaturated flow shall also be discussed in this lecture. Now, to begin with, we will start with the maximum discharge of steam, then we will develop general relationship between area velocity, and then we will discuss supersaturated flow. Now, for the flow through a nozzle, we already know that the pressure ratio P2 by P1 is equal to 2 by n plus 1 raised to power n upon n minus 1. For this pressure ratio, the discharge is maximum. We know the discharge equation m by A2, that is equal to 2 n over n minus 1 P1 V1 P2 by P1 raised to power 2 by n minus P2 by P1 raised to power n plus 1 by n. Now, this is the equation for the mass flow rate through the nozzle. This is for pressure ratio when the discharge to the nozzle is maximum. Now, putting this P2 by P1 here, we will be getting m by A2 is equal to under root 2 n over n minus 1 P1 by V1. Now, P2 by P1 is 2 by n plus 1 raised to power n over n minus 1 multiplied by 2 by n. And this one is minus P2 by P1 raised to power 2 by n plus 1 raised to power n over n minus 1 multiplied by n plus 1 by n. Now, this n will be cancelled out, this n will be cancelled out, and we will be getting m by A2 as 2 n over n minus 1 P1 by V1 2 by n plus 1 raised to power 2 by n minus 1 minus 2 by n plus 1 raised to power n plus 1 divided by n minus 1. Now, we will not further simplify it, because once we know the value of n, we can find the mass flow rate for a cross section area A2 or cross section area A. So, for dry and saturated steam, when the dry and saturated steam enters the nozzle and it gets expanded, the value of n is 1.135. Now, if we put the value of n is equal to 1.135 here, we get mass flow rate as 0.6356 A2 under root P1 by V1. Mass flow rate when n is equal to 1.3, when steam is superheated when entering the nozzle, then m is equal to mass flow rate is equal to 0.6673 A2 P1 by V1. We are getting this expression by putting this value of n in this equation. So, this is the maximum mass flow rate while flowing through a nozzle. Initial conditions are P1 and V1. We will keep on putting the value of different P1 and V1, we will be getting a different maximum mass flow rate through the nozzle. Now, we will develop a general relationship amongst the velocity and pressure and density Now we will be developing a general relationship between the parameters. It is a relationship between area and pressure. Mass flow rate through the passage is AC by V. Mass flow rate is area into velocity divided by specific volume, right? Okay. Now A plus del A, C plus del C divided by V plus del V is equal to AC by V. Now we can write V A del A plus V A C plus V A del C plus V C del A plus V del A del C is equal to ACV plus AC del V, right? You just simply multiply this with this and this with this one. Now here we will be cancelling this by this AC del V, okay, and this can be taken as 0 because the del A is infinitesimal again and del C also infinitesimal, so this will be tending to 0. So the final expression is VA del C plus VC del A is equal to AC del V divided by VAC divided by VAC divided by VAC will give us the expression del C by C plus del A by A minus del V by V is equal to 0. Because in this expression, this VA will be cancelled here, VC will be cancelled here, AC will be cancelled here. Okay, and if this delta C, delta A and delta V are tending to 0, then we can always write DC by C plus DA by A minus DV by V is equal to 0. Now, all of us know that PV raised to power n is equal to, constant, not 0, constant. PV raised to power n is equal to constant. Or we can write in differential form dP by P plus n dV by V is equal to 0, or dV by V is equal to minus dP 1 by n dP by P. That is one thing. Second is, we already know that C dC is equal to minus V dP from momentum equation. So dC by C is going to be dC by C minus V dP by C square. When we take this, dC is equal to minus V dP by C and dC by C is equal to minus V dP by C square. Now plus dA by A minus dV by V is equal to minus, and then if we are putting this, then it is going to be plus 1 by n dP by P is equal to 0. we will take dA by A on left hand side is equal to V dP by C square minus 1 by N dP by P. Right? Now here dA by A can be taken as 1 by N dP by P inside the bracket, because this we are taking out. So inside the bracket will remain N PV by C square minus 1. Now dA by A is equal to 1 by N dP by P. Now NPV, if you remember, the sonic velocity of steam is going to be NPV. For gas, it is going to be gamma RT. So this is nothing but sonic velocity, and this is going to be A square by C square minus 1. There is a term which is known as, it's a dimensionless number which is known as Mach number, and Mach number is actual velocity divided by sonic velocity. So this expression can further be written as dA by A is equal to 1 by N dP by P 1 by m square minus 1. Now this is the governing equation. Now this equation has two differential terms which are dA and dP. Let us start with the flow through the nozzle. Flow through nozzle. When there is a flow through nozzle, this dP will be negative, because in the direction of the flow, there is a fall in pressure, but due to this fall in pressure, the kinetic energy is attained by the fluid. So in the direction of flow, there is a drop in the pressure. So here dP is going to be negative. Now dP is negative, or we can say this dP is negative 1 by m square minus 1. The velocity of steam is less than the sonic velocity, or the C is less than A, or m is less than 1. When m is less than 1, this expression is positive, right? And dP is negative. So dA by A is negative. This expression I will write again. When m is less than 1, this expression is positive, because this is greater than 1. 1 by m square, m is less than 1, 1 by m square is greater than 1. And this expression we have already assumed negative. So dA by A is going to be negative. It means up to the sonic velocity, or less than, for velocity less than the sonic velocity, if you want to draw the shape of the nozzle, the shape of the nozzle is going to be like this. Now second case, m is equal to 1. When m is equal to 1, dA by A, this expression is 0. 1 by m square is 1, and this expression is 0. When this expression is 0, dA by A is also 0. It means there is no change in velocity, no change in cross section area for a sonic flow. Third one is when m is less than 1. M is 0, we have already discussed. M is less than 1. m is equal to m is less than 1 we have discussed. Now the flow is supersonic, m is greater than 1. When m is greater than 1, this expression is negative. When the m is greater than 1, then m is greater than 1, this 1 by m square is less than 1 and this is going to be negative. When this is negative, dA by A is going to be positive. It means when the flow is supersonic flow, the passage has to be divergent. dA by A is positive. So there are three cases we have discussed: when velocity is subsonic, velocity is sonic, and velocity is supersonic. When the steam velocity is subsonic, the passage is converging. When steam velocity is sonic, there is no change in the cross section area. When the velocity is supersonic, the passage will become divergent, and this is a very interesting situation. It means in this area, the velocity will increase and cross section area will also increase. But normally what happens when we deal with the fluids, when we reduce the cross section area, the velocity increases. But in supersonic zone, if you want to increase the velocity, we will have to increase the cross section area. And in most of the nozzles, you will observe that these two lengths are not equal. The converging length is shorter, much shorter than the diverging part of the nozzle. It is something like this. Reason being, in the diverging part, if we take this angle, there is a limiting value for this angle, and that limiting value is 20 degree. Right? If this angle is more than this, separation of flow, because the fluid is diverging, this is a diverging passage. So separation of flow will take place from the wall, and this will reduce the efficiency of the nozzle, because this will incur losses in the flow of the fluid, and this will reduce the efficiency of the nozzle. So now normally this angle, because 20 is the limiting value, 12 to 15 degree, the value of diverging angle is taken. And since we know this diameter, throat diameter, we know the exit diameter, that is how the length of the diverging section is decided. This angle is known to us, this diameter is known to us, this diameter we have already calculated while designing the nozzle, and this will decide the length of the nozzle, length of the diverging part of the nozzle. Now let us take case of diffusers. Now in diffusers, the kinetic energy is converted into the pressure energy, right? So velocity is reduced, in diffusers the velocity is reduced and the pressure is increased. So in diffusers, this dP is positive, right? Now dP is positive. Let us take case of the diffusers. This diffuser, there is a pressure rise, so dP is positive, m is greater than 1, entry is supersonic in diffuser, it is reverse of the nozzle, entry is supersonic, m is greater than 1, right? This is going to be negative, right? When this is greater than 1, and no, not positive, sorry, this is positive, not negative, just a minute. When m is greater than 1, then this is negative, right? dP by P is positive, so dA by A is going to be negative. Same process we will adopt here. dA by A is going to be negative, right? When m is 1, then there is no change in the throat area. When m is less than 1, subsonic, right? When m is less than 1, in that case, this is positive, and this is going to be positive. right? So this is how we decide the shape of nozzles and diffusers. There is a phenomena for during the flow inside a nozzle which is known as supersaturated flow of the fluid. In supersaturated flow of the fluid, what happens? Suppose if I depict expansion in a nozzle on a enthalpy and entropy diagram, let us say inlet is supersonic, superheated, the steam is superheated, right? And this is state 3, which is exit state. In fact, the condensation should start after this point. This is saturation point. So during expansion, the moment the state 2 is attained, the condensation should start. But this does not happen. There is a lag. And there is a lag, and condensation starts after further expansion up to state 3, 4, let us say 4. Then why this happens? This happens because the condensation is a process which cannot occur spontaneously, right? And the time spent by the fluid inside the nozzle, because the velocities are of the order of, let us say, 700 meter per second. So such a high velocity, the fluid is flowing with such a high velocity, the time spent by the fluid inside the nozzle is almost tending to 0. Almost tending to 0. Right? Very less time is spent inside the nozzle. And during that time, if this state arrives, the condensation of the fluid cannot take spontaneously, because for condensation some nucleation site is required, right? After certain value, I mean initially condensation does not occur, but after this state, because the state is continuously changing, when the state comes, when condensation takes place without any nucleation site, that happens when the density of fluid is almost 8 times the density of the saturated vapor. So while expanding from this point to this point, condensation will initiate at this point. This lag is known as supersaturated flow of the fluid. The fluid is supposed to, some condensation was supposed to take place inside the fluid, but it is not taking place. The condensation is initiated at this point, right? Second thing is, the vapor has, the molecules have random energy, random kinetic energy, and to contain, because when the fluid attains this state, the intermolecular attraction is sufficient to confine the molecules inside a droplet, and the droplet formation starts. Now due to this supersaturated flow, there is a very interesting phenomena, that is increase in the mass velocity. Normally there is a 2 to 5% friction losses during the flow inside a nozzle, but due to this phenomena, supersaturated flow, there is increase in the mass flow rate inside the nozzle. So normally it is compensated, the flow, the losses due to friction are compensated by increase in mass flow rate in the nozzle. If there is no friction loss, in that case increase 2 to 3% increase in the mass flow rate through the nozzle will be observed. Now, in addition to this, there are certain effects of supersaturated flow of fluid in the nozzle. That is, number one is reduced heat drop. The heat drop is reduced, and this reduces the velocity as at exit is reduced. So heat drop is reduced, corresponding velocity is reduced, and number 3, final quality of the vapor is increased, and entropy is also increased, right? Entropy is also increased. That is the effect of supersaturated flow through the nozzles. And this has a bearing on the discharge through the nozzles. Now, this line where the condensation is initiated, this fictitious line is known as Wilson line, right? And if we draw the constant pressure line on the graph, these are the constant pressure lines, right? This is constant pressure line, and this is the constant pressure line for, so let us say this is 3. So this is the constant pressure line is equal to P3. Now, if we extend the curve of this to in this direction, this one, so this will follow this the process will follow this curve, right? And here the steam or the vapor will be dry and saturated. Instead of state 2, the vapor will be dry and saturated at state 2 at pressure P3. This is all for today. Thank you very much.